Okay, we have two more examples I'd like to take a look at before we finish the section. So here's an example where we say, let's let A equal Q at R, and that's going to be the area of a circle with a radius of R centimeters. And what I'd like to know is, what is the radius if the area is 25 square centimeters? So the first thing I need to remember is the formula for the area of a circle, and hopefully if I asked you, what is the area of a circle, you would all say to me, oh, area is pi multiplied by the radius squared. So notice I've written that down here. So now the question asks us, what is the radius? So I need to figure out what the radius might be. So again, what's the radius? If the area is 25. So the question is, what's R going to be when A is 25? So what I did was I put 25 in for my A, and there's my pi R squared. Now remember, I want to solve for R. So I need to get the R by itself. So I divided both sides by pi, so that gives me R squared equals 25 divided by pi. And then remember, when I have a square, in order to solve for the variable, I need to take the square root. So I take the square root of R squared and the square root of 25 divided by pi. Notice, by the way, that technically when we put on the square root, remember there's two items that would square to get us 25 over pi. One would be positive and one would be negative. So technically it's plus or minus the square root of 25 over pi. But of course we know the negative does not make sense, because remember our goal is to find the radius, and so we'll just include the positive answer as our answer in the problem. And so we get R equals the square root of 25 divided by pi. That's the exact answer. If we wanted the approximate answer, if we put that in our calculator, we would end up getting approximately 2.821. And notice when I did this, once again, I don't use the equal sign, I use the approximately equal to sign. So if you put it in the calculator and it does not come out even, we want to make sure we use the approximately equal to. So again, I could do this graphically. So in y1, I would put the left-hand side of the equation, y1 is 25. And in the calculator in y2, I would put the right-hand side of the equation, pi x squared. Graph both of them and find the intersection, and you'll notice when I find the intersection, I get the x value. X is 2.8209479 out to several decimal places. The nice part is, notice that checks. Again, I'm going to expect you to do the algebra, but the calculator is a nice little check on something like this. Now the last example, and this is actually an example that appears on page 71 of your textbook. What we have is we have a graph here, and what we have is a person who's actually driving toward a store and potentially back home from the store. And what we have along the x-axis, or the independent variable axis, is time in minutes, and along what you think of as the y-axis, or the dependent axis, is the velocity toward the store. So notice when the velocity is above the t-axis, when we're in that beginning time period, that's when the person is actually traveling to the store, and when it's below is when we're traveling home from the store. And so what I want to do is use this to determine these ideas. So if I wanted to compute v at 2, remember 2 is the input, and so I would go over to where 2 is, and I would read up and I'd get 20. And if I were interpreting that, I would say after 2 minutes or in 2 minutes, the man, happens to be a man situation, is traveling 20 miles per hour, and because we're above the axis, we're heading toward the store. V at 14, same deal. We would go over to 14, read up, and guesstimate. And we might be off a little bit. It doesn't look like it's quite halfway, so I call it 34. So in 14 minutes, the man is traveling 34 miles per hour. And again, he's still traveling toward the store. V at 17, well, that falls between 16 and 18, so we're right here. And notice we're at 0. So in 17 minutes, the man isn't traveling any velocity toward the store. He, in fact, is actually at the store. V at 28, same idea. Go over to 28, read down. Looks like it's about halfway through. So I happen to say, oh, I think it is. So I guessed negative 35. So in 28 minutes, the man is actually traveling 35 miles per hour. but he's not traveling toward the store, he's traveling away from the store. Or in other words, he's traveling what we would expect is back toward home. Then we have one more piece of this. Suppose I want to know and solve for t when v at t equals 10. Now notice 10 is no longer the input, 10 is the output, 10 is the velocity. So what I would want to do is read across my velocities and find all of the values that produce that output of 10. And if I do that, I guesstimated, I said, well, 0.5 might be closer to well, maybe it's about 0.5. And you have to guesstimate a little bit. T equals 4, a little bit after 6, so I called it 6.5. And then one more time between 14 and 16, I guessed 15.5. Okay, well, take a look at the other examples in the book and make sure that you go and do your homework, and we'll be talking about any of the problems that you have, anything that's not clear from the notes in class.